Okay, folks, this is the second recording. It's recording number 2 for section 4-3. And where we left off was we were talking about this conditional probability. And the concept is, I would say, pretty easy. What we're basically saying is that we have two events in sequence. One happens after the other. And the second event depends upon the first event. Okay? So the convention that the author typically uses here, but he's not consistent, is he'll use A and B. So you'll see, like right here, the probability, the conditional probability that an event B occurs after an event A has already occurred. So he's putting them in alphabetical order. That kind of helps keep track of things, but he's not consistent about it. Okay, so here's the formula. If they're independent, the probability of A and B is simply the probability that A occurs. That happens first, so that has to happen first. Then the second thing that happens is that B occurs given that A has already occurred. Okay, so let's see if we can come up with an example here that sort of makes sense here. And now, as you can see, he changes the notation. It kind of makes you crazy. So what I did when I was trying to figure this stuff out is I switched everything back to the A and the B. So let's see if I can figure this out as we go along here. So we have 5.2% of the people are unemployed, and then 33% of those who are unemployed received unemployment benefits. So what has to happen essentially is you have to be unemployed, okay, first, and then if you are unemployed, there's a certain probability that you're going to be collecting unemployment benefits. So now we're picking a person at random, find the probability that he received unemployment benefits, okay, if the person is unemployed. Okay, so it's unemployed benefits, so you get the benefits, and unemployed. Okay, so what's basically happening here is he's using U for unemployed before he was using A. That's the first event. Okay, so if you want to change that, on your paper, that'd be maybe a good idea. So the first event is being unemployed, and then you get the unemployment benefits. So what's our formula? The first event is being unemployed. The second event is collecting the unemployment benefits given that you're unemployed. Okay, so it's just plugging in the formula. The probability of getting the benefits given that you're unemployed is given to us as being 33%. The probability of being unemployed is 5.2%. So the two of them together, you multiply them. So first thing that happens is you're unemployed. The second thing that happens is that you get the benefits. Okay, so it's kind of like the first rule. You have one thing happening, then you have the next thing happening, but the second thing that happens is dependent upon the first thing happening. Okay. All right, let's see if we can come up with a better example here. Okay, drawing cards, you can figure it out just by observation here. The probability of getting 3 jacks in a row, getting an ace, a king, and a queen in order. Let's do B here. Okay, so the first one you get in order, 4 out of 52. Okay, you do not replace, according to this. It says do not replace. So it's 4 out of 51 to get the king. Now, see, there's still 4 kings, but there's only 51 cards. The next one is getting a queen. You did not replace, so there's still 4 queens, but you did not replace, so it's 4 over 50. So you multiply all that out, and you get this this number. Okay. All right, so I hope I help you understand that. You're going to have to look at that a little bit, but it's not as hard as it looks, honestly. And then he talks about how you can use tree diagrams. It kind of helps you. And we'll see here in this next example why this helps. So we've got the balls again, got the red balls, the blue balls, and so forth. Okay, so I can't get the whole thing on this screen, so I'm hoping you guys are looking at your book to help you follow along here. Okay, so now we're going to talk. I apologize, during the little break there I had to move around here a little bit. Let's see if we can get back up here to where we're at. Give me a second here. Okay, so here we are at conditional probability. Okay. So what we got going on here is just some arithmetic. All right. So we have multiplication rule number 2 here, where we talked about the probability of A and B occurring is equal to the probability of A occurring times probability of B occurring, given that A occurs. Okay, sorry about that. Yeah, in the bottom here, if you look on page 189, the formula that he's using, the language he's using, and I want to use the same language for consistency, on the top is always going to be the number of outcomes in whatever it is that you're looking at. So, up here it's the number of outcomes, A and B. And on the bottom it's the number of outcomes in the sample space. That's always what we're talking about. That's on page 189. That's the formula for the classical probability. So the number of events in whatever the number of outcomes in some set, and on the bottom is the number of outcomes in the sample space. Okay, so if we're talking about the number of outcomes of A and B, that's right here, A and B. Okay, in the denominator, what's the total number of outcomes in the denominator? Well, what's our new sample space? Well, A has already occurred. So A is our new sample space. So instead of being what we had previously, a big sample space, now we have a small sample space. A has already occurred. So that's what he's saying here, okay? He says, listen, you got the areas here. The reasoning here is that if you assume A has occurred, that's my new sample space. And then that's the calculation. For the next calculation, A is the sample space. It's the denominator, that's the bottom guy, of the probability fraction. The numerator, P of A and B, represents the probability of the part of B that is contained in A. So see, there's an intersection here. These guys right here, they're in B, but they're also in A. They're in the intersection, okay? So the probability of A and B becomes the numerator of the probability fraction, and that imposes a condition that reduces the sample space. So let's see if we can make this sense out of this. and we're going to use chips, black and white chips, instead of using the balls. Now we're switching over to the chips. Okay, so we got a box. They have black chips and white chips. We take the chips out. Now it's very important to notice that we are talking about it's without replacement. We are not replacing the chips. Okay, so probability of selecting a black chip and a white chip is 15 over 56. That's what he's telling us. The probability of selecting a black chip on the first draw is 3 out of 8. Find the probability of selecting a white chip on the second draw, given that the first chip selected was a black chip. Okay, so it's just kind of a little bit of a formula here. The probability of the second event given the first event occurs. So that's the probability of getting a white given that the black has occurred. And I wish this guy would not switch the notation, but he did. So the probability of getting a white given that you've already selected a black, well, the probability of getting a black, that's always in the denominator. That's easy peasy, right? You're assuming that you already picked the black. That's part of the problem. So that's in the denominator. In the numerator is a probability that you get a black and a white chip. Okay, and that is given to you right here. They give that information to you. They're just trying to get you to understand the concept here. Okay. Okay, so these are all kind of basically the same. I'm going to let you work your way through these. My advice on these, man, oh man, my advice is always the same. Write them out in detail, because if you can't write them out in detail, if you can't explain it to yourself or to an intelligent 13-year-old, you're not going to be able to do the problems on the exam, okay? It's just using the formula. And the formula, if it were me, if I were the king, the way I would write the formula is I'd say the probability of the second event given the first event has occurred is the probability of both of the events divided by the probability of the first event. To me, talking about it as first events and second events and talking about it as being both events, that makes more sense to me. Otherwise, this notation absolutely gets in your way. It absolutely gets in your way. So try to be aware of that situation. Okay, so I want to move on because I need to get into this other concept here, this probabilities of at least. The concept here is we're going to use this complementary probability that we talked about previously, okay? And remember, the complementary means everything else, okay? So if you're talking about the probability of men in the classroom, you know, and you don't know, well, I'm not going to go down that path. Let's just stick to their examples. So you pick 3 cards from an ordinary deck. You replace each card, so there is replacement. That's important. What's the probability that they'll get at least 1 heart? Okay, so it's the event that we're talking about here is at least 1 heart. So that could be, it could be 1 heart, 2 hearts, 3 hearts, or 4 hearts, right? Okay. Or correction, it could be 1 heart, 2 hearts, or 3 hearts because you're drawing 3 cards. Okay, so the concept here is that's too hard to figure out. So what we're going to do is we're going to say, well, the E that I'm looking for, the event, at least 1 heart, E bar is that there's no hearts are drawn. So it's a lot easier to figure that out. The chances of getting no hearts, if there's no hearts, what does that mean? Okay, if there's no hearts, that's 39 cards. It's 39 cards that are not hearts. That's the other suits, right? So 3 draws is 39 out of 52, 39 out of 52. Multiply all that out is 27 over 64. So the probability of E bar is 1 subtract this, okay? Okay, now that's the typo I wanted to tell you about. See, it shouldn't be probability of E bar here. It should be the probability of E. And I'm sorry for the typo, but it's not my fault. So the probability of E is 1 subtract the probability of E bar. So that probability E bar comes from right here. 1 subtract that gives me this. Boom, there it is. Okay, the next example, probability of getting at least 1 6. It's a lot easier to figure out the probability of getting 0 6s. So the probability of getting at least 1 is 1 subtract the probability of getting none. And the probability of getting none, 5 over 6 times 5 over 6 times 5 over 6. It's because there's 4 tosses. So it's 1 subtract this number, and that gives you that. So it's very clear that this is a much easier way of doing it. Okay, I'm out of time. Read read the book.